So in previous lectures, we talked about Turing machines or algorithms for regular languages, Turing machines for regular languages, and the regular languages. We looked at the following. Not for regular languages, in fact, for properties of regular languages. We talked about A, accept DFA, which takes a DFA and a string and decides whether this DFA accepts the string. And we talked about E, which is empty DFA, and EC, which is equivalent DFA. And for these problems about regular languages, could we find Turing machines or not? Yes. So we found Turing machines. So all three were decidable. So for each one of these, we described a Turing machine or an algorithm that is guaranteed to terminate in regular time, in finite time. And Turing machines for context-free languages, that was the focus of last lecture, context-free languages. So we talked about A, CFG, E, CFG, and equivalence of CFGs. So this is the acceptance given a context-free grammar and a string. Determine if the grammar generates this string. And was this decidable or undecidable? Yeah, it was decidable. And E, context-free grammar, determining if a context-free grammar, the language of a context-free grammar is empty or not. Was this decidable or not? Decidable. Yeah, so this was decidable. Now, equivalence of context-free grammars, was this decidable or not? No, it was not decidable, so undecidable. In fact, that was the first undecidable language that we studied. So undecidable language means a problem that cannot be solved using algorithms. So there is no algorithm. You cannot come up with an algorithm that will take two context-free grammars and determine if they are equivalent or not. Okay? Of course, we did not prove this, but we just attempted to use the same technique that we used for regular languages. We tried to use the same technique, but we failed because... Why did we fail to use the same technique that worked for regular languages? Yeah, because context-free languages are not closed under intersection and complementation. So today, we're going to look into Turing machines for Turing machines. So accept Turing machine, empty Turing machine, and equivalence of Turing machines. So now a Turing machine, you can think of a Turing machine as a program. In fact, in this lecture, I'm going to focus on the intuition. So I'm going to focus on, I will most of the time view a Turing machine as a program, not as an abstract Turing machine. So that it's, this presentation is more intuitive. So ATM is, you are given, it's the language where you are given a Turing machine, M, and a string W. So M is a Turing machine, and W is a string, and M accepts W. Okay, and ETM is checking if a Turing machine is empty. So this is going to be M. M is a Turing machine, and L of M equals phi. And this is the equivalence of Turing machines. So it's M1 and M2. You are given two Turing machines, M1 and M2. M1 and M2 are Turing machines, and the language of M1 equals the language of M2. In fact, we're going to focus on this today. So today we will focus on showing that ATM, which is determining, given a Turing machine, determine if it accepts a given string or not. Now let's think about this in terms of programs, not Turing machines, so that it makes more sense and it's more concrete. So before I start, can anyone describe this problem in terms of programs? So a Turing machine, think of a Turing machine as an algorithm, and an algorithm is implemented using a program, using some programming language. So program. Think of the Turing machine as a program written in some programming language, in a general purpose programming language, or in fact a Turing complete programming language. So when we say a Turing complete programming language, is a programming language that can do that has all the features that a Turing machine has. Of course, a modern programming language is much easier to program compared to a Turing machine. The Turing machine is a primitive theoretical model. It's not something that can have any practical value today. But a program written in one of the languages that we are familiar with, like C, C++, or Java, general purpose programming language, you can think of it as a Turing machine. It has all the features. You can do with it anything that a general purpose computer can do. So thinking of a Turing machine as a program, what does this problem mean? What is it like in terms of don't use Turing machines, use programs, use the word program. What does this problem ATM mean? It means you are given, so we are looking for a program that takes another program, okay, and an input to that program, and determines if the output is going to be accept or reject. So the programs that we're talking about here are programs whose output is yes or no. So we're talking about programs that solve decision problems. So at this point, we're talking about a program that takes an arbitrary input, and the output of that program is yes or no. So like a program that takes a graph and determines if the graph is connected or not. Or a program that takes a graph and determines if the graph has a cycle or not. Okay, or a program that that takes two finite automata and determines if they are equivalent or not. We know that we can write such a program. We can write a program that takes two finite automata and determines whether they are equivalent or not. But we know that we cannot write a program that takes two context-free grammars and determines if they are equivalent or not. There is no algorithm for this. So we cannot write a program that takes two context-free grammars and determines if they are equivalent or not. So now what about a program that takes another program and determines if that program is going to accept a given string or not? So there is program M that takes input W. And this program M, the idea is that M is a Turing machine or a program written in a general purpose programming language. So M is a very general program. It can have anything in it. That's why, analyzing this program is hard. So this is basically ATM is the program analysis, a program analysis tool. So we'd like to have an analysis tool, analysis program that takes M and W. So it's an analysis program that takes as input another program M and the input W to that program. And this analysis program is going to tell us if we input W into M, the output will be accept or not. Okay? So now the problem here is that can this analysis program even determine if program M is going to halt or terminate on input W or not? So what if, not all programs are guaranteed to terminate within finite time, right? So there are programs that can run into infinite loops. So basically the challenge in writing such a program analysis tool is in determining if program M, when given input W, is going to terminate within finite time or loop forever. Now suppose that, of course, for any program M, if program M is simple enough, then the program analysis tool is going to know that the program M is going to terminate within finite time. Let's focus on determining if M is going to terminate in finite time or not. If M doesn't have any loops, then we know that M has no loops and no recursion. Then we know for sure that program M is going to terminate in finite time. Now, what if M has something like this? For I equals 0, I less than 1,000, I plus plus, and then do something. Or X equals Y plus, or some array reference, or whatever. So to analyze a program like this, now imagine that you are writing an analysis tool that will take this program and determine if this program is going to terminate within finite time or not. Now, if this was the only loop in the program, will you able to determine? Yeah. So this is the only loop, and this only loop in the program has a finite loop bound, right? So it's for an easy program like this, we'll be able to determine if that it will determine within finite time. Now, what if we have this? Now, the thing is that we're looking for an analysis tool that can analyze a general program, right? So a general program may have something like this. Now, if you have somewhere x equals something, 100 or 1,000 or whatever, then again, this is something that you can analyze. Now, we're trying to analyze the program at compile time without running it, without running the program. So we have the notion of a static analysis of a program and a dynamic analysis. Now, what's a static analysis? Analysis at compile time, or analysis without running the program, without running the program. And the dynamic analysis, you run it and analyze it at runtime. Now, how many people have used program analysis tools? Okay, so what program analysis tool did you use?
Clean tidy.
What's that?
Clean tidy.
Okay, checking for, what does it check for?
Code smells in C++.
Okay.
It's like extended warnings.
Okay. Is it static or dynamic?
Static.
Yeah. So it's static. It means that it takes your code and analyzes your code and gives you some information. Like, checking for uninitialized variables, for example. Okay. Or checking for out-of-bound memory accesses. Now, some of this can be done with a static analysis, but not everything can be done with a static analysis. Why? Because the behavior of the program is input dependent. Now, what if you have something like this? And then if 2 times w plus 3 is greater than 5, break. Now, can you determine with a static analysis, without running this program, whether this will terminate in finite time or not? In fact, can you determine if this condition will ever become true? Why not? Because it depends on W. It depends on the input, and we don't know what that W is. So here, this is an expression that uses W. And this expression determines if the program will terminate in finite time or not. But things cannot be, may not be as simple as that. You can have something like, f of x, function, it calls a function f that takes W. And then this function can be anything. This is a general purpose programming language. We're trying to develop a tool that can analyze any program. And then in this f can call g, and g can call h, and h can call whatever. So there can be a whole sequence of function calls. So function f is going to call function g. And then function g can call function h. And you can have a whole sequence of function calls. So this is, the bottom line is that with a static analysis, without running the program on input W, you will not be able to determine if this program terminates in finite time or not. If this program is guaranteed to terminate in finite time when you input W or not. Right? So then, in fact, this is the ATM problem. It's in order to determine if a Turing machine accepts a string or not, you will need, an important part of this is determining if that Turing machine is going to halt, is going to terminate within finite time or not. And with a static analysis, I hope that I convinced you intuitively that with a static analysis, you cannot determine if a program can terminate within finite time. You will need to do a dynamic analysis. And a dynamic analysis, in this case, would be just, this program analysis tool is just going to run M. It's going to invoke M on W. So, a program can run another program, right? So how many people have written programs that run other programs? Yeah, so you can use, on Linux you have the exec function call that can execute another program. And so there is a system call that will allow a program to run another program. So if this program analysis tool is going to run this program M, and then to determine if M is going to terminate within finite time or not, now is this a decider? Is this a Turing machine that decides the problem? No, it doesn't decide the problem, because if M runs into an infinite loop, M will never return. Right? Now we know that if M doesn't run into an infinite loop with input W, we know that M is going to return, and then here print yes. So we're trying, this analysis program is trying to determine if M terminates in finite time or not. Now, it's going to print yes if M terminates. But if M does not terminate, this yes will never be reached, right? So this is exactly what it means for a problem to be Turing recognizable, but not Turing decidable. So this problem is Turing recognizable, but not Turing decidable. Again, a Turing machine is a program. So in other words, you can write a program, you can write an analysis program that takes another program and determines if it terminates in finite time or not. If that program terminates in finite time on that input, the program will print yes, and it will terminate in finite time. But if this program runs into an infinite loop, then what? Then the analysis program itself will not terminate. So that's why this is the intuitive explanation that this problem is not Turing decidable. You cannot come up with a Turing machine or an algorithm or a program that does this, that can take an arbitrary program that's written using the same general purpose language. So here the idea is that this program M is written in the same general purpose language. And because it's written in the same general purpose language, it can have anything. So it can have this function f. Its termination is dependent on f. And f is dependent on g, and g is dependent on h. And this dependence chain is not bounded by anything. Okay. Now, this is determining if it holds or not. But here, this is you look at the return value, the result. So solving this problem, the acceptance problem, if M or if result equals accept, else reject. So this program, this analysis program on the board, this is a dynamic analysis tool that takes any program. It simply runs that program and looks at the result. If the result is accept, it accepts. If the result is reject, it rejects. But the problem with this is that we are not guaranteed that this if statement here will ever be reached. Because if this guy runs into an infinite loop, if will never be reached. Yeah, so that's the dynamic analysis. The dynamic analysis is just run the program that you are trying to analyze. So you run it, but again, the key issue is that it's not guaranteed to terminate. It may run into an infinite loop. And if it runs into an infinite loop, you will never know if it accepts or rejects string double. So this is an intuitive explanation. So there is an actual proof in the book. So we're not going to do the proof, the abstract proof for this. You are welcome to look at this. But of course, you are in the tests and in the homework. You're responsible only for what we explain in class. So in class, we're not going to do the abstract proof. You're only responsible for understanding this intuitive explanation. Any questions on this? Okay. So the bottom line is, if someone asks you to run a tool and to write an analysis tool that will take an arbitrary program and determines if that program has an infinite loop in it or not, you will not be able to write such a tool.